So good evening everyone. So maybe we'll start for today. Today what we'll discuss is we'll go through a few questions, and primarily we would want to understand, like, till now we have already understood CISO systems and their basic properties and how to control CISO systems, how to place eigenvalues and those kinds of stuff. Those things we have done quite well till now. So now we'll dive a little deeper and we'll see how to do disturbance rejection in state space systems, and with very simple extra terms and additions to the normal control system that we had earlier, how we can reject disturbances. Then we'll consider the case of multiple input systems, and finally we'll look briefly into a linear quadratic regulator problem, which is a simple case of standard optimal control problems. All right. So with that, maybe we'll start for today. Yeah. So tracking a constant reference signal in the presence of disturbances under state feedback can be achieved by which of these? So any guesses for this solution? If there are any guesses, please type your answers in the chat box. So let us take a look at how we can get ahead, around the disturbances that are present by adding some more feedback mechanisms. So consider this first. Yeah, this is x dot. So we'll get x here, which is the state of the system. Then from the state, we can obtain the output y, which is c times x. Now, to complete this loop, we get in a feedback a. We send in a feedback a, and there is a summer here. So if there is no input, then x dot is simply equal to ax, and this becomes a autonomous system. All right, but let's assume we have some input u, and u must be multiplied with b. So here I have u, but instead of u, what is happening is a little disturbance is creeping through, right? So this u plus w will now give me some u bar, which is my new input to the system. All right, then so in standard state feedback, what do? We get the state, have some gain matrix, feedback gain matrix k, and then send it to as the for the input, in a feedback form. Okay, so this will be minus, and here typically we would have had some regulator or whatever reference value we wanted to track. Okay, but what we'll do now is we'll add a few more terms. Okay, just bear with me. Yeah, okay. So this is what we have. All right. So this is my reference input, which I am taking an error with the output that I am obtaining. Why? Because I want my output to track some reference input. So I'll feed their error as the input to this overall system. Okay. Now what is happening? We'll take a term XA here. Sorry, XA dot. So here I'll get XA. Then this is multiplied with some gain. And then this thing is input into this remaining system. And what is it? And along with this, I kind of give a feedback of k. Alright. So here I have some xa minus kx. Yeah. Let's no, not xa. This is some v, which is ka into xa. This is ka into xa. So here I'll give v, and here I'll get minus kx. So what this is in some senses, I'm feeding an error as the input, which corresponds to this v is like some reference signal that kx should satisfy. Okay, so v minus kx is fed into this as u. Then I have noise coming in, and the net thing becomes some u bar, right? So this is what we have. And there is a result which states that if a comma b is controllable, and if the transfer function c si minus a inverse b has no zero at s equal to 0, then all eigenvalues of the new A matrix can be assigned arbitrarily. Okay, this is the result that we have. So one thing that we need is a comma b has to be controllable. If it is not, then we cannot do anything. And the next thing is the transfer function of the original system that should not have a 0 at s equal to 0. So why this is necessary is if there is a 0 for this system without this noise, let's say, for this system, if there is a 0 at the origin, then this is just a pole that we are like multiplying, and the pole also is at the origin, so there will be a pole 0 cancellation. Alright. So we want no 0 of the transfer function to be at origin. Then what we can do is that all the eigenvalues of the new A matrix can be assigned arbitrarily. So what is the new A matrix? So what we do is we now take the new state vector as x and xa stacked together. Alright. So now let's take some time to, I'll copy this here. So let's take some time to determine the state space form of this x tilde. So x tilde will be some a u, or some other terms might also come. So just this is just like solving the block diagram. So let's do that for a couple of minutes, then we'll discuss the solution. Okay. Yeah, anyone did it? So do you need some more time or do we discuss? Okay, let's take some more. Okay, sure. So first, tell me what is XA dot in terms of the inputs that are coming in. One is the R thing that is coming in, the reference input that we supply, minus Y, which is R minus CX. Okay. And X dot is your own standard thing given by AX plus BU bar, which is AX plus BU plus BW, right? Because X dot is this AX plus BU bar, which is further W plus U. So now I can stack this X dot XA dot equal to, now what is X dot? It is first term, we'll just write in terms of X and XA. So X dot is just A and 0 here. XA dot on the other hand is here, it is minus C, here 0. Then we have B0 U plus 0 1 R plus B0 U plus 0 1 R plus B0 W. Okay, now we can write some state feedback U as KA minus XX. So this gives me, so this is A tilde. Okay, so A tilde will now become, so this whole thing X dot XA dot is equal to, now becomes A minus BK 0 minus C. Here we'll get minus BK A. Yeah, then we'll have here 0 and this will be XA. Yeah, and the output will be just C0 XA. So this becomes my new LTI system for the whole thing. And this, we saw that there is a result which says that even with disturbances, now I can assign the eigenvalues of the new A matrix arbitrarily as I want to. So, which amongst these things was necessary for getting the system under control? Like, what was the new thing that was done? Any guesses now? You can drop it in the chat. Yes, what kind of action are we adding on the system to help reject disturbances? So this is the new part, right? And taking this fictitious state and introducing these kind of actions. And this is just an integral action, right? Because here 1 by s is just an integration. So an integral action is required to track a constant reference signal in the presence of disturbances. Is this clear, whatever we discussed? Please let me know if there are any doubts. So if not, we'll move. Okay, yeah, we'll move ahead. Now, given a system X dot, it's a multiple input system. So there are two inputs and there is a 2 cross 2 state like B matrix. Now using MATLAB, compute a state feedback gain matrix for the MIMO system using the cyclic method. And we are asked to take V as 1 by 1 and 2, like the vector 1, 2. And we want to find the resulting feedback matrix for the closed loop eigenvalues at lambda equal to -4 and -5. So let us start by seeing the cyclic method. First, for the cyclic method, we need to ensure whether the provided A is cyclic or not. Okay. So how do we determine whether a given matrix A is cyclic? It has to the Jordan form of the matrix should be such that every distinct eigenvalue has only one Jordan block associated with it. So first, let us transform this A matrix into its Jordan form. How do we do that? First, tell me what are the eigenvalues. Yeah. First, let us find the eigenvalues of A.
Sir, plus minus root 2 I.
Plus minus root 2
I.
G. So then does that yeah. So does that mean the matrix is cyclic?
Sir, don't know.
Okay. So A has the eigenvalues plus minus j root 2, which means if you diagonalize A, then what? You will get eigenvalues at the diagonal elements and zeros at other positions, right? If you had a repeated eigenvalue, let's say root 2 root 2, then what would have happened? You would have had to check whether there are any Jordan blocks, multiple Jordan blocks, or what kind of structure we have. But since here we just have distinct eigenvalues, we clearly know that if we diagonalize the matrix A, I'll get eigenvalues only at the diagonal position. Okay. So A is a cyclic matrix. So first step is over. Now the second step, what it does is, here we'll use, so in cyclic design what we do is we use two primary results. First is, so okay, this one result itself is enough. If n dimension p input pair a comma b is controllable and if a is cyclic. So these are the two things that we need. A comma B pair is controllable and A is cyclic. Then for almost any P cross L vector V, the single input pair is controllable. The single input pair A comma B V is controllable. So what does this statement say? If we have an n-dimensional, let's say in this case it is a two-dimensional system, we have a two-dimensional P input pair. So how many inputs do we have? Two. So two-dimensional, two input pair, like two-dimensional state, two input, and this pair of A comma B, A and B. So if that is controllable, and further if A is cyclic, then for almost any vector, for almost any vector V of size P, the single input pair A comma B is controllable. So what is the single input pair? So what we are doing is we are converting the multiple input problem into a single input problem. Okay. So A remains the same, but instead for U, what do I give is like this BV. BV now becomes my new B matrix. So we have verified that A is cyclic. This is done. Now let us verify whether A comma B is controllable. Let us find out the controllability matrix for this AB system. So what is C?
Sir, 1241.
Okay, how do you get that? What? Wait. Which row, which column?
First column 1 and 2. Second 4 and 1.
No, but uh, okay. So what is the controllability matrix? This is B, A, B, right? For a two-dimensional
Yes.
system. So first place B matrix should be there, right? So here I should have 1001. Then AB I'll multiply, which will get me what? 0, 2, 1, 0. Yeah, because AB is the yeah, identity. So is this clear?
Sir, but new matrix B is BV now.
No, no. But see, first we have to check that this A comma B itself is controllable or not. Then only we'll decide whether this is controllable or not.
Okay, sir.
Yeah. So because if this is controllable, only then we can guarantee that for almost any vector V, this pair is controllable. So just we are just verifying. But here we have clearly that this obviously is a rank 2 matrix because no two rows or no two like at least two columns are independent because we have the identity here. So this is clearly rank 2. Then yeah. So now we have to design for the single input pair system. Okay, so now A comma BV, which means what is BV? BV I just get as 1, 2 because B is identity. So now this is my new system that I want to control. So let's say this becomes x dot equal to ax plus b bar u bar. Okay, where this is b bar. So for this, I want my lambda to be at -4 and -5. So let us do the standard procedure. Let us take u bar is equal to sum minus kx, then x dot equal to a minus b bar k x, and I need this matrix to have these eigenvalues. Okay, so that is the standard procedure. Let us solve that. So we have a minus bk 0210 minus b bar into k. Let's take k1 k2. Yeah, so this is minus k1 2 minus k2 1 minus 2k1 minus 2k2. So what are its eigenvalues? Let's solve that for 2 minutes. So what are the eigenvalues? So okay, let's not find the eigenvalues. Let's just find the characteristic polynomial. What is it?
Sir, lambda square plus lambda into 2k plus k
2k1,
2k 2k2 plus k1
2k2 plus k1,
plus bracket close
bracket close,
plus 4k minus 2
4k 1 or 2.
1 1 4k1 minus 2.
Okay. So now we want the eigenvalues to be placed at -4, -5. So this has to be same with this equation. So doing that, we'll get what? We'll get 4k1 equal to 22. So k1 is 5.5. And by that logic, k2 is 9 minus 5.5. So 3.5. And k2 is thus 1.75. Okay. Is this clear? Correct?
Yes, sir.
So let us just do this entire thing in MATLAB. Before that, so what we did is we had originally our control was of two, like it was two inputs only, but we decomposed it into one input thing. So we were giving AX plus BV minus BVKX, which means U is minus VKX, which means this matrix 1, 2, K we found out 5.5 and 1.75. So that means this is 3.5. Is this correct? Just verify once. Okay. So this matrix will give me the feedback matrix K for the two input system. So this is how we neatly like change the multiple input back to single input. Then just a little trickery and we get the feedback matrix for the the multi-input thing. Now let us do this in MATLAB. Yeah, my screen is visible to you.
Yes, sir.
Yeah. So we'll do it. So we had this A matrix 0 to 1 0, B matrix as identity. So first we get this the eigenvalues of A, where this did we get this, or I think we got something else. 0 to 1 0. Okay, so then we find the controllability matrix, which is clearly rank 2, which is a full row rank. So the thing AB is controllable. Then we take the vector V as specified for this question and just use the MATLAB place command to place the poles of the system A, BV at -4, -5, which results in K being 5 and 2. Okay, I think we made a mistake somewhere along. So that's why MATLAB is pretty helpful. And A minus BVK is now this matrix. This is the closed loop matrix. Okay. And if you find its eigenvalues, you can see that they are at -5 and -4, which is what we wanted it to be. And so we just verified that this new thing. And finally, we have to, uh, so if, just a minute, V and K. So V into K will now give me this. So this is the thing that we were asked for to find the resulting feedback matrix for the closed loop eigenvalues given by -4 and -5. Is it clear?
Yes, sir.
Yeah. Okay. So this I think we briefly discussed last class as well. Given this matrix, which of the following statements is or are true? is this matrix cyclic or Hurwitz? So what do you think are the answers? Yes, any guesses? Okay, then we just recall the definition of a cyclic matrix. Matrix is cyclic if its characteristic equation is equivalent to the minimal polynomial. But let us leave this definition aside and use another equivalent definition which is easier to check, which gives that as matrix A is cyclic if for all distinct eigenvalues, the resulting uh, Jordan form has only one. So basically, every distinct eigenvalue has only one Jordan block associated with it. Okay, so in this situation, clearly this is in a Jordan form because there are no, like, yeah, you see, this is just eigenvalues on the diagonal element and just this one corresponding to the Jordan block. Now, by this definition, do you think this matrix is cyclic?
Yes, sir.
Yeah. So that means this is a cyclic matrix. So which kind of matrix would not have been cyclic is if let's say we had 3 3 1 0 3 3. Okay. If we had a matrix of this kind, then here you see that this is one Jordan block and then these are separate. Okay, so corresponding to each distinct eigenvalue, which here only is 1, 3, there are two Jordan blocks associated. One is this kind, and the other is a normal eigenvalue just on the diagonal. Okay, so in some situations, the system might have an A matrix given by this. In that case, it is not a cyclic matrix. So here we have verified that A is cyclic. Now, what is a Hurwitz matrix? So if you remember the Routh-Hurwitz criterion, I guess it is named after him because so any matrix is Hurwitz if it has only strictly negative eigenvalues, right? The real part of eigenvalues are negative. So then the system is completely stable. So such kind of a matrix is a Hurwitz matrix. So here we know that the eigenvalue is 3, which is clearly a positive value. So the matrix A is cyclic but not Hurwitz. So this is correct. This is wrong because A is cyclic. This is again wrong. The matrix A only has one eigenvalue. This is correct. Matrix A has repeated eigenvalues. Right? Is this question clear?
Yes, sir.
Okay. Now, which of the following statements is or are true for a MIMO system? Okay. So, eigenvalues of the open loop system can be placed at arbitrary positions using a unique state feedback matrix. Now, what do you think? Is this true? Can we always use only a unique state feedback matrix to place the eigenvalues? Try to think about it. So try to think in terms of the cyclic method that we used. Using that method, can we always guarantee that we'll find only one state feedback matrix to obtain the desired eigenvalues?
सर नहीं समझ आ रहा.
Okay, so let's think of let's go back to this question. Okay, where we started? Huh. So I think the mistake that we did here was the eigenvalues. They would be lambda minus 2 minus 1 lambda equal to 0. So lambda square minus 2 equal to 0. So lambda is plus minus root 2. No, okay. Now, uh, so here in cyclic design, see that we need this some v. Well, our result says that for almost any v, I can find a pair which is controllable, a comma bv. And what is the state feedback matrix? It is essentially you write the controller sum u is equal to minus kx, right? So this capital K is the state feedback matrix. But while using cyclic design, what do? We we say that a comma bv is controllable, so we'll control that system. But by that nature, you get where did we get? Yeah, you get this term, right? So ax minus b capital Kx. So this capital K is given by v into small k. V small k. Right. So if I take a different value of v, then I get a different value of k, and the net this matrix itself will change. Is it correct?
Yes, sir.
Yeah. So let us try that. Give me a minute. Yeah. So I'll share my tab once again. So we do this. A B find its eigenvalues. Whatever controllability matrix does not change, this does not change. But now let's take instead of 1, 2, I take 3, 2 as the V matrix and place, I want to place my eigenvalues at the same position. So I'll place them. So this is what I get. But earlier, if you remember, I do 1, 2, then the solution would be 5, 2, the small k matrix. And this was the VK which we got. Right, 5 to 10 4. Now by changing this to 3 2, let's say, I obtain K as something else and this new state feedback matrix as something else once again. Correct. So there need not be a unique state feedback matrix for, yeah. So there need not be a unique state feedback matrix for our system. Give me a minute. Yeah. So that is what we saw here. Yeah. So this thing is verified, the eigenvalues of the open loop system can be placed at arbitrary positions using a unique state feedback matrix is a wrong presupposition. Let's check the second one. There exists more than one feedback gain matrices which can place the eigenvalues at arbitrary positions. So this is what we verified just now. We saw in MATLAB that by changing the value of the V vector in cyclic design method, we can not only we'll get two different feedback gain matrices, and that is perfectly fine. There is no uniqueness for MIMO systems. Ah, Now coming back to Lyapunov based method. So if you remember, so I'll just go through the procedure once. Yeah. So Lyapunov, what he says is, again we'll consider an n-dimensional p input pair A and B, and I want to find a P cross N real matrix K such that A minus BK has any set of has any set of desired eigenvalues. But one exception is this desired set cannot contain any eigenvalue of the matrix A. Right. So what does that mean? Let us check this. Pole placement using the Lyapunov method requires that the closed loop poles do not coincide with the open loop poles. So what are the open loop poles? Can someone tell me? So the open loop poles, okay, let's say you had a system. So typically you have an integrator x dot x a, but you take a word k here. Okay. So what we are saying is, if we did not have this feedback thing, then the system would have been open loop, right? Then what is the transfer function from u to the, let's say the output is here, it is given by this part without any feedback. So that means this is the open loop system. So the open loop poles corresponds to this system. And what is this system given by? X dot equal to Ax. So the open loop poles corresponds to the eigenvalues of the A matrix, and while the closed loop corresponds to some A minus Bk x eigenvalues of this matrix. So pole placement, and what did we discuss here for Lyapunov method? N-dimensional P input pair A comma B, then we can find a real matrix K such that this closed loop system has any set of desired eigenvalues, but it cannot contain any eigenvalue of A. So that means the pole placement using the Lyapunov method requires that the closed loop poles do not coincide with the open loop poles, which is the eigenvalues of A. Right? And using Lyapunov's method, poles can be placed at the position of eigenvalues. This is wrong. So for this guy. Is it clear?
Yes, sir.
Okay, just a minute. So we now have a system, linear system. This is a single input, single output. So case A matrix, B matrix, C matrix. Let P be some symmetric matrix assumed as P1, P2, P2, P3. Select the correct statements regarding the algebraic Riccati equation considering Q equal to I and R equal to 1. So can first someone tell me what is the algebraic Riccati equation? Okay. The algebraic Riccati equation is given by A transpose. Okay, let's just go into some theory for this. So assume there exists symmetric P matrix which is a solution which solves the algebraic Riccati equation ARE, for which the matrix A minus P R inverse B transpose P is a stability matrix. Then the feedback control given by feedback control law U equal to minus kx given by k is equal to R inverse B transpose P stabilizes the closed loop system while minimizing the LQR objective J equal to 0 to infinity Y transpose QY plus U transpose RU dt. And here the ARE is given by the matrix equation A transpose P plus PA plus C transpose QC minus PBR inverse, just big terms, V transpose P equal to 0. Okay, so is this result clear? Just the statement of the proof. Sorry, just the statement. We need not go into the details of the proof, but what the statement says is, I have some given LTI system A, B, C matrices are given, and I want to find a control law that minimizes this objective over all time. Okay, so what is this objective? So Y transpose, let's take a single input, single output system. Then, yeah, so then what? C is, sorry, single input, single output. So Q is what? Only, just 1 minute. Mm, Okay, not Q, but okay. Let's take a single input, single output. Y is the output, and let's take Q is identity. Then what does this give me? Yeah, y we can write as cx. So this will be what? Y is equal to y transpose x transpose c transpose q c x. Okay, let's just think about the. So let's say I take y square. Okay, and say I want to minimize this over all time. So what does this mean? Minimize this. So what would y square be significant of? Like what would it indicate? In some sense, if I want to minimize y square, then what I want to do is I want to keep my output at a low amplitude as much as possible. The sign need not matter, but I just do not want my y to be blowing up. Okay, let's say I have a y curve given by something like this and another y curve given by something like this. So if I'm minimizing y square like this, which one would be preferable? The blue one or the red one?
Red one, sir.
Red one.
Yes, sir.
So when we are writing this term, this Q is just like a weighting. So if I had a single input, single output thing, everything is a, let's say a scalar system, then we won't have this identity matrix here. Just let's say y, let's say 1. But instead of 1, let's say I had some small q thing here. So what does that mean? I am doing q y square is my minimizing term. So that means this q matrix is just like a weighting matrix, just like a weight, like we do a weighted sum or something like that. There what the weights are just kind of how much weightage you put on the that particular variable. And similarly, U transpose RU also corresponds to your uh, okay, 1 minute. Yeah. So U transpose RU also corresponds to kind of the same thing what happened with the output, but also with the input. So along with keeping the output at a lower level as much as possible, we also do not want the input to be very high. Okay, so we want both the input and output to be in some reasonable range. And these Q and R matrices are up to us to find out like the weighting that we want to give them. I might say that I I'll allow some input to go a little higher than some bound, but my output has to be completely below some level. Then my Q matrix will kind of represent a higher weightage and R will represent a lower weightage. On the other hand, let's say I do not have a very powerful motor, then let's say I have a motor as an actuator and I do not have a very powerful motor, I have just a very small one. Then what I can do is I can weight the R matrix highly. So that would mean you like the amplitude of the input increasing would be much more detrimental to my cost than the amplitude of output increasing. So by settling a trade-off between Q and R, I can effectively I can effectively decide what exactly is my objective here. All right. So this is the concept behind LQR control, right? And what we are saying is this control law where K is given by this and the P matrix satisfies this ARE, then this objective is minimized. Okay, let's not go into the proof or any other details, but that is what the statement says. I give a control U equal to minus kx, give where k is this, and P satisfies this algebraic Riccati equation. Then, and further, if this matrix is a stability matrix, then my LQR objective is minimized. Okay, so then let's find out. This is A matrix, this is B matrix. First, let us solve the algebraic Riccati equation. Okay, I'll copy these values over to here. A is 1 0 0 minus 1, B is 1 0, C is also 1 0. So let us write the ARE and try to solve it. A transpose is nothing but the same thing. P plus PA plus C transpose Q is identity. So I have 1 0 0 0 is equal to that PBR inverse. So this is C transpose C, okay? And other side, if we go P1, P2, P2, P3, B, B transpose, R is just 1. And this is again P. Okay, so let's solve for this. First, tell me what should the RHS be?
So
Hmm?
right hand side, so P1 square, P1, P2 side.
Uh, we'll get a 2 cross 2 matrix here.
So right hand side,
हाँ राइट हैंड साइड में 2 cross 2 मैट्रिक्स होगा.
Yes, sir. P1 square,
P1 square,
P1 P2 कॉलम में
P1 P2,
और फिर ऊपर P1 P2
P1
P2
P2,
स्क्वायर.
P2 square. Correct. So this is the right hand side. Okay. Then simplify the left hand side into one matrix.
so
Hmm.
फिर मेरा सर आ रहा है P1 plus 1,
2P1 plus 1.
0.
Call this
नहीं सर, राइट साइड में
0.
सर 0,
Mm-hmm.
सर -2P2, -2P3.
Minus 2P3. Okay. So when we equate these two, क्या आ रहा है हमारे पास? दिस implies first is p1 p2 is 0. Okay, then p1 square equal to 2p1 plus 1, and
Yes, sir.
finally p2 square is equal to minus 2p3. So tell me what p1 p2 p3 will solve these three equations. Is any solution?
So one.
Okay.
सर गलत आ जा रहा है।
क्या आ रहा है?
सर P1 की वैल्यू सर क्वाड्रेटिक बनी, दो वैल्यू आई है 1.61 एंड माइनस 0.61।
Okay.
सर सेटिस्फाई नहीं। सर 1.61
1.61 and
ऐसा माइनस 0.61।
uh, तो फिर एक मिनट. So we had three equations. Okay, first is this quadratic p1 square minus 2p1 minus 1 equal to 0. So p1 is what? 2 plus minus root of 4 plus 4 by 2. So 1 plus minus root 2. ये मिला था.
Yes, sir.
फिर इधर से अब p1 is clearly not equal to 0. So p2 equal to 0. And finally इधर से p3 equal to 0. Correct?
यस सर।
So अभी next thing to remember is कि the control law given by this, like first p निकालना है जो ये satisfy करता है, फिर verify करना है कि a माइनस ये मैट्रिक्स स्टेबिलिटी मैट्रिक्स है. So a minus b R inverse B transpose P. Okay, so R is 1, so this means this is equal to A minus 1 0 0 0 P, which is, so find this matrix for A का वैल्यू हमको पता है 1 0 0 minus 1, B is 1 0 and P इधर से मिला, so P is 1 plus minus root 2 0 0 0. So what is this A minus B matrix? This entire thing.
सर
हम्म
फिर क्या करने के लिए सर बोलने में ध्यान नहीं दिया।
अभी A पता है, B पता है, P पता है।
यस सर।
अब ये मैट्रिक्स
लेट्स फाइंड करें।
वेरीफाई करना है कि स्टेबिलिटी मैट्रिक्स है, तो फर्स्ट फाइंड द वैल्यू।
ओके
यस, तो इससे हमारा आ रहा है माइनस प्लस रूट टू 0 0 minus 1. So is this a stability matrix?
सर आइगन वैल्यू निकाल के जज करेंगे।
हाँ, तो इसका आइगन वैल्यूज क्या क्या है? So what are the eigenvalues of this matrix? डायरेक्ट डायगोनल मैट्रिक्स है तो पता चल जाएगा। हाँ,
प्लस लेंगे तो 7/5 आ रहा है और -1 आ रहा है प्लस रूट टू लेने पे।
प्लस रूट टू लेंगे
तो सर आइगन वैल्यू 7/5 आ रहा है और -1 आ रहा है।
7/5 कैसे आएगा?
सर 7/5 मतलब वैल्यू बता रहे हैं सर।
नहीं, बट 7 लाइक डायगोनल मैट्रिक्स। हाँ हाँ, तो 1.4 मतलब रूट टू ही है।
यस सर।
हाँ, तो eigenvalues are minus plus root 2 and minus 1.
-1. Yes,
तो
sir.
अगर 1 plus root 2 लिए तो माइनस रूट टू आएगा विच इज अ स्टेबिलिटी मैट्रिक्स, और अगर 1 माइनस रूट टू लिए तो प्लस रूट टू आएगा। करेक्ट, क्योंकि यहाँ पर माइनस हो रहा था तो 1 माइनस 1 प्लस रूट टू होता है माइनस रूट टू, बट 1 माइनस 1 माइनस रूट टू आ जाएगा प्लस रूट टू। तो 1 प्लस रूट टू है स्टेबल वाला, तो हमारा p हम लेंगे 1 प्लस रूट टू 0 0 0। तो now let's go back to the question. Select the correct statement regarding the algebraic Riccati equation. With p2 equal to p3 equal to 0, the Riccati equation is not solvable. But हमारा solution तो आया था with p2 equal to p3 equal to 0. So this is wrong. Then there exists a positive definite solution p of the Riccati equation. So we solved the equation. So obviously there exists a solution. फिर the matrix p given by 1 plus root 2 0 0 0 0 solves the Riccati equation. ये भी आया था हमारा, करेक्ट। फिर तो ये भी करेक्ट है। फिर द मैट्रिक्स ए माइनस बी पी ट्रांसपोज पी इज हर्विट्स फॉर पी इक्वल टू ये। तो ये भी हम वेरीफाई किए कि 1 प्लस रूट टू वाले के लिए ये हर्विट्स हो रहा है, फॉर ऑल अदर केसेस मतलब जो दूसरे वाले केस के लिए 1 माइनस रूट टू के लिए वो हर्विट्स नहीं होता। तो दीज थ्री आर द करेक्ट ऑप्शंस। ओके, तो एलकेआर का कॉन्सेप्ट रफली समझ आ गया।
Yes, sir.
Okay, so now we move on to the Lyapunov design method. So we are now given a MIMO system, A matrix, B matrix, and it is designed to obtain a state feedback matrix such that the closed loop eigenvalues lie at -3 and -4. Now we use the Lyapunov equation method to compute a feedback matrix K such that to compute a feedback matrix, and what should it be? Okay, remember that this, okay, sorry, this is, so this matrix was the solution we got using the cyclic design method in the second question. Okay, but now we'll do Lyapunov design method. So can someone tell me the steps? So first I'll just mention the problem. Consider an n-dimensional P input pair AB. Here AB. We want to find a K matrix such that A minus BK has any set of desired eigenvalues. Okay, but these desired eigenvalues should not have any eigenvalue of A. So now tell me the eigenvalues of A first, because that is something we need to verify. Find the eigenvalues of A.
Sir, 1, 1.
So A has eigenvalues 1, 1. Then first step is select an n cross n, select a, here in this case 2 cross 2 matrix F such that with these desired eigenvalues. Okay, So what is f? We can directly take f as a diagonal matrix as this. So this has the desired eigenvalues -3 and -4. Okay. Next step is, so we have now found out f. Now we have to select some arbitrary k bar, some k bar, such that f transpose comma k bar transpose is controllable. Okay, k bar is sorry, f is -3 0 0 -4, and this is also f transpose. So we have to select some k bar. Now tell me a very simple and trivial k bar such that this is true.
सर से यहाँ ऐसे स्टार्ट करें, ऑप्शन चेक करके स्टार्ट करेंगे।
No, no, no. के बार निकलना है, ये के नहीं।
सो बाहर कैसे निकालेंगे?
नहीं, गेस करना है, मतलब वी कैन टेक एनी के सच दैट दिस इज कंट्रोलेबल। तो कोई भी के जिससे ये कंट्रोलेबल हो रहा है वो ले सकते हैं हम। बट मैं बोल रहा हूँ कि कोई एक आसान केस सोचो जो कि बहुत सिंपल होगा और ये कंट्रोलेबल होगा। पहले बोलो कि ये कंट्रोलेबल होने के लिए क्या कंडीशन है। कंट्रोलेबिलिटी मैट्रिक्स लिखेंगे तो ये जो मैट्रिक्स है इसका डायमेंशन क्या होगा, ये पूरा मैट्रिक्स।
सर कंट्रोलेबल होने के 2 into 2 होना चाहिए।
नहीं नहीं, ये मीमो सिस्टम है तो लाइक एफ ट्रांसपोज 2 × 2 है, तो ये भी 2 × 1 होना चाहिए और ये भी, तो ये भी 2 × एक मिनट, अच्छा, p × n होना चाहिए ये, तो ये भी 2 × 2 ही होना चाहिए बिकॉज वी आर डीलिंग विद अ मल्टीपल इनपुट सिस्टम। ठीक है, तो एंटायर चीज क्या हुआ, 2 × 4 हुआ ना।
यस सर।
सो इफ वी टेक k बार एज आइडेंटिटी तो ये क्या हो जाएगा, 1 0 0 1, ये हो जाएगा -3 0 0 -4। तो ये पूरा चीज रैंक 2 बाय डिफॉल्ट हो गया।
Yes, sir.
यस, सो रैंक 2 बाय डिफॉल्ट मीन्स, जस्ट अ मिनट, या, सो वी कैन टेक k बार एज आइडेंटिटी। फिर नेक्स्ट स्टेप है, so we took k bar. Now third step is solve unique t for this equation at minus tf is equal to b k bar. तो इसके लिए t के लिए सॉल्व करना है। So what is the solution? So I'll just write this 1 2 0 1 t. Let's take t1 t2 t3 t4 minus t1 t2 t3 t4 और f था -3 0 -4 is equal to b identity into identity क्योंकि कई बार भी आइडेंटिटी लिए थे। तो ये टोटल आइडेंटिटी हो गया। तो फाइंड यूनिक वैल्यूज फॉर T1 T2 T3 T4। सो लाइक वो ARE सॉल्व किए थे वैसे ही सॉल्व करना है। जस्ट 4 इक्वेशन आएंगे, 4 अननोन से, वी जस्ट हैव टू सॉल्व देम। So this becomes
सर 1 मिनट.
okay.
So T1 equals to 1.5.
T1 equals to
1.5.
1.5,
T2 is equals to 0.88.
0.88,
T3 is 0.
T3 is 0.
T4 is 1.33.
Okay.
Yes, sir.
Same आ रहा है?
Yes, sir.
Okay. So T matrix is 1.5, 0.88, 0, 1.33. Correct. तो just a minute. So ये फर्स्ट एलिमेंट देखते हैं, ये क्या T1 प्लस 2 T3 और इधर का फर्स्ट एलिमेंट होगा -3 T1 प्लस 3 T1 इज इक्वल टू 1। हाँ बट T1 तो 0.25 आ रहा है।
Sir, 0.25. Yes, sir. Sir, T1 0.25.
Okay, let's just
T3 0.
okay, I'll just write these equations that I got. T1 plus 2 T3 plus 3 T1 equal to 1. T2 plus 6 T2 plus 4 T, sorry, 62 plus 2 T4 is equal to 0. T3 4 T3 equal to 0 and 5 T4 equal to 1. तो ये हमारे 4 इक्वेशन आएंगे for the 4 elements of the matrix. So this gives me T as 0.5, sorry,
0.25.
T as 0.25
Sir,
point,
T2.
हाँ बोलो,
Sir, T3 0.
हाँ
Sir, T4 1/5 मतलब 0.2.
0.2,
और सर ये मतलब 0.8.
ये 0.08,
0. Yes.
yes, okay. सो ये टी मिल गया। अभी ल्यापनोव इक्वेशन मेथड से हमारा जो के मैट्रिक्स फीडबैक मैट्रिक्स है दैट इज गिवन बाय के बार टी इनवर्स। ओके, सो के बार इज आइडेंटिटी, सो दिस इज जस्ट टी इनवर्स। तो टी इनवर्स कर देने पर हमको कंट्रोल लॉ मिल जाएगा जिससे आइगन वैल्यूज डिजायर्ड लोकेशन पे हो जाएंगे। ओके, so let's just do this with MATLAB once. Before that, let's just try this question. This concept is clear, right?
Yes, sir.
Okay. So just a few steps, I'll reiterate them. First step is this. Select an F matrix that has the desired eigenvalues, just that they should not be equal to the A matrix's eigenvalues. Then next step is K bar, find K bar such that this thing is controllable, which we just took identity. Then third, solve for unique T satisfying this equation. And then finally, your K is given by K bar T inverse. Okay. So then the final question, then we'll go to MATLAB. So select the correct options out of the following. A feedback invariant functional only depends upon the control input and not the initial state. So by definition, a feedback invariant some h depending on x and u. If h is a feedback invariant, then by definition it means that h does not depend on the particular value, particular function u, but only depends on x at time 0 given the value of x at as time goes to infinity should go to 0. Okay, this is the definition of a feedback invariant functional. So by that definition, this option is incorrect. Then the LQR weighting matrices can be arbitrarily selected and does not affect the value of the cost function. But we saw that the weighting matrices Q and R, they actually depend affect the value of the cost function, because the cost itself is given by x transpose qx plus u transpose ru dt. Okay, then so this is also incorrect. Then a matrix with non-unity algebraic multiplicity of all the eigenvalues is cyclic. Now we cannot say what will happen in this case, because algebraic multiplicity का मतलब है कैरेक्टरिस्टिक इक्वेशन में कितने बार रिपीटेड रूट्स आ रहे हैं. सो इफ कैरेक्टरिस्टिक इक्वेशन इज लैम्डा माइनस वन होल स्क्वायर इंटू लैम्डा माइनस टू, देन algebraic multiplicity of 1 is 2, algebraic multiplicity of 2 is 1. Okay, तो ये कितनी बार रिपीट हो रहा है एज अ रूट, हियर 1 है, that gives me the algebraic multiplicity. And if algebraic multiplicity is greater than 1, then I cannot guarantee whether the diagonal form will be Jordan or non-Jordan and how the things will happen. Okay, so let's take for example matrix 2 2 1 0 0 0 2 0 0. तो ये matrix में there is only one eigenvalue 2. So but the thing is third order, so characteristic equation will be of third order. Okay, so characteristic equation is third order, तो मतलब lambda cube कुछ एक आएगा and you are getting only one solution to, मतलब कि lambda minus 2 whole cube equal to 0 is the characteristic polynomial. So if this is the characteristic polynomial, then clearly algebraic multiplicity for all eigenvalues is greater than 1. It is not 1, non-unity. बट ये मैट्रिक्स साइक्लिक नहीं है, सो दिस इज अगेन रॉन्ग। और ये साइक्लिक क्यों नहीं है? क्योंकि इसका एक जॉर्डन ब्लॉक इधर है और एक इंडिपेंडेंट है। सो नन ऑफ दीज ऑप्शंस आर करेक्ट, सो नन ऑफ द अबव। ये एक थियोरेटिकल क्वेश्चन था, क्लियर है?
Yes, sir.
Okay, so then finally we'll go to MATLAB for the previous problem. So we had A matrix and B matrix given by these, right? And उसके eigen values are given by 1 and 1 of the A matrix, which we found out. So now we'll take an F matrix given by this, right, which contains the desired eigenvalues. Now I'll take my K bar as identity and check the controllability matrix of the pair F transpose and K bar transpose. Okay, so this is my controllability matrix, and clearly you can see that the rank of this controllability matrix is 2. Then finally we found out T using by solving those equations, which is 0.25 minus 0.08, 0 and 0.2. Then we, just for checking, what were we solving? AT minus TF is equal to B K bar. So B इधर, so we need to check we need to check that T satisfies AT minus TF equal to B K bar. तो B और K bar तो आइडेंटिटी है, तो B K bar आइडेंटिटी है। तो लेट्स चेक व्हाट इज AT minus TF with this T. So turns out it is identity only. So this T is the unique solution to this equation. And finally T inverse. So T inverse is given by 4, 1.6 and 5. So it was one of the options for finding, and this is what we wanted to find out, right? The equal. This is P1. We want to find K state feedback matrix given by K given by K is equal to K bar into T inverse. Okay, so K bar is identity, so it is just inverse of T, which is given by this matrix 4, 1.65. Okay, is it clear?
Yes, sir.
Okay, so then with that we'll stop for today's session.